Shut up and sit down. Tom, you ready?
Yes.
All right, so next up, Tom McDermott, N5EG. Title of his talk is Using TangerineSDR to Build a Personal Space Weather Station.
Thank you, Steve. Scotty did a great job explaining the modularity of the TangerineSDR. In this talk, we're going to look at the first choice implementation for the personal space weather station. So we'll look at which specific modules we're going to use to build the personal space weather station. So just kind of to recap a little bit of what Scotty said, TangerineSDR is a modular SDR radio, whereas the personal space weather station is a specific set of those modules. Scotty described probably 25 or 30 different modules. We're going to pick 3 of those and build the personal space weather station out of that. So the idea here is we'll start out with a very narrowly defined set of functions, and we'll go into implementation of this personal space weather station. And then with time, we'll start adding new modules and other things. But we need a small detailed set so that we can write software, we can do implementation. If we try to start out with 25 modules, we won't get the project finished. And so we'll have one. So the personal space weather station is a set of specific modules plus the firmware that goes on the FPGA, a 3-axis magnetometer, the local host computer plus storage plus software that Bill is working on, and then a central server run by the scientists that collect and manage the data from these instruments. The personal space weather station implementation philosophy is science is basically done in kind of 2 different categories. One is synoptic or long-term observations mode, basically space weather climate, and then event modes, which are weather. We anticipate that the very first space weather station will have a specific set of capabilities, but that over time, as new research projects come along, we'll want to augment the capabilities, put on some new functionality. And so the modular nature of Tangerine is amenable to saying we want higher clock accuracy for some specific research study so we can plug in a new module. And so over time, we'll be able to augment the capabilities of the personal space weather station, but we still need to have a kind of regular, stable, predictable measurements over time in order to monitor space weather. In both use cases, instrument design and reuse is very attractive. We want the ability to upgrade portions of the design for targeted event studies, but we need to annotate the data with metadata that says what instrumentation was used to collect the data, what kind of clock module was used to collect the data, which RF module was used to collect the data, so that we annotate metadata when we collect the information. And 5 years from now, when someone asks the question, well, what kind of clock performance did you have when you measured that data? We'll have enough metadata in there we can go back and say when it was recorded, what kind of instrumentation was it recorded with. We have these 72-bit unique IDs that will let us go in and figure out what kind of module was used to take that measurement. So we don't want to start over from scratch each time, because if we decide we want a new, Space Weather Station 2, which has a little bit different kind of performance characteristics, if we have to go back and then reinvent every single component in there, then it's a huge new project for every research campaign. And we'd rather be able to say, well, we have almost all of the pieces already, we just need to change the clock module, and the software just has to change to anticipate a new clock module. So don't start over from scratch every time. Reuse most hardware, most software, most firmware, even if we make a change. And by doing that, we have cost containment because we only update the specific pieces. And if you want Space Weather Station 2, you only have to change out those pieces that you need to augment from Space Weather Station 1. We spent some time last fall going over what are the requirements for Space Weather Station version 1. And there is about a 10 or 15 page document that we put together. We got all the research scientists and the TAPR folks on a series of conference calls, and we put together a requirements document. This is kind of a summary of what's in that requirements document. Number one is it's got to be low cost. Every conversation we have comes out with it's got to be low cost. The key is that the first iteration needs 2 HF receivers from about 0.1 to 30 megahertz with reasonable dynamic range. We set up the spec to have about 88 dB of dynamic range. The noise figure needs to be less than about 10 dB. The receiver needs very low phase noise. We need the ability to calibrate the receiver amplitude. So a lot of receivers today, the signal is S7. Well, what does S7 mean? Well, S7 sort of means, 6 dB per S unit. Well, what's S0? Who knows? So we're actually going to try to calibrate the receiver amplitude. We have 2 receiver channels on the first version, and we need tight phase coherence between those channels because we want the ability to do interferometry across the 2 channels. That is, we can phase correlate received information and do things like beam steering of the received antennas. And to do that, we have to very carefully control the clocks. We want to do high accuracy time stamping of the samples, and we need high RF frequency accuracy. So if we want to measure WWV, we have a highly accurate frequency reference, and then we can look at the Doppler shift of WWV down to a fairly tight frequency accuracy. We want to be able to timestamp within about plus or minus 50 nanoseconds of time so that the receiver channels data will be actually time-stamped within about 50 nanoseconds of time accuracy. Right now, the initial objective is during normal GPS reception. There are ionospheric events that will drive GPS receivers off into the weeds. And so if we have a very difficult GPS reception event, that 50 nanoseconds of time-stamping accuracy is going to go way off. If we need better than that, then there'll be a phase 2 clock where we put on a higher performance clock module. And then we need 3-axis magnetic field measurements, and the initial spec is 13 nanoteslas of resolution and about a 1-second update rate. The magnetic field sensor in your smartphone is orders of magnitude worse than this, so this is fairly high precision. High precision enough that we have to worry about things like we can't use steel pins to plug the modules together because the steel in the pins will actually degrade the magnetic field sensor. So this is a block diagram of the Personal Space Weather Station version 1, and it uses Scotty's data engine with the pair of gigabit Ethernet. It uses the 2 receiver module, which has got 2 antenna inputs. It uses a GPS-DO and a synthesizer, and that, of course, has got a GPS antenna hung on it. The magnetometer has to be remoted out away from this collection of modules. And so what we have is what we call the local cable extender and the remote extender, and then the magnetometer plugs onto the remote extender. And we can accommodate up to 100 feet of cable in between the 2 units, so we can put the magnetometer outdoors somewhere in a plastic enclosure 100 feet away from this particular receiver module. The data engine then talks over gigabit Ethernet to a single board computer with storage that Scotty was describing, and there's an internal switch here so that it can send data up to the central server. So version 1 is this particular receiver module, this particular GPS module, this particular data engine, this particular single board computer, and this particular magnetometer set. And we will nail down, you must implement and choose these particular modules for the version 1 of the Space Weather Station. That's to keep the software folks from going totally crazy. The dual receiver, this is a block diagram of the dual receiver module. So this is the RXM 5001D. You'll use that module for the Space Weather Station. The block diagram, it has got two antennas. And they go through a relay into this plug-on fixed RF filter that Scotty described. Most likely that's going to be an AM broadcast band reject filter, or it's going to be a shortwave notch filter. It could be an FM broadcast reject filter. We expect that there'll be some high amplitude stuff that we want to get rid of. Then a programmable attenuator. We're looking at what we use here. There's some dual 14-bit ADCs that are fairly cost effective, and with newer silicon technology, much lower power than the A to D converters that were used in OpenHPSDR. And there's an ADC driver, whether this is two single channel or one dual channel. We're still going through the part selection process. One of the unique things here is we have a broadband noise source, and that will go through a relay, and periodically we can connect the receiver input to this broadband noise source. It has a known amplitude distribution over frequency, and so we can periodically switch the receiver down to the noise source and calibrate the input amplitude on the receiver. And since it's broadband, you can see the output and say, what plug-in RF filter do I have on the board, because I can see a big notch in the noise if I've got a particular one. If I have the attenuator set, I can see the impact on that noise source. So it allows us to validate the quality of the data coming in, because we can see how we're equipped, how we're set up. There's this identification prom on the module that has a unique 72-bit serial number for the module, and that describes which module in this, so that when we collect data for the Space Weather Station, we'll know which module is plugged in. We'll know if the firmware on the FPGA is the right firmware to talk to that module, so that we can make sure that we try to gather quality data. The dual 14-bit ADCs provide a very wide data bus down to the data engine, and there's an SPI interface that allows us to configure the A to D converters and their properties. This dual ADC needs a clock that is a very low jitter clock, because jitter degrades the sensitivity of an ADC, and has excellent frequency accuracy and stability. So that will come off that GPSDO module. We tried to estimate, the question is always how much receive sensitivity is enough. When you ask the scientists, more is better. And, but you have to attach a dollar sign to more. And so we tried to estimate the noise figure. Tom Holmes, who was not able to attend DCC, whoops, let me go back, hit the wrong button, provided this module, which was developed by the Midwest VHF-UHF Society, and it provides a 5 dB excess noise ratio, which is 5 dB above thermal noise, and over the VHF and UHF frequency range. And so I basically tacked a 0.1 microfarad capacitor across the existing 10,000 puff coupling cap and moved its bottom end down into about a megahertz or so. Well, it's not too bad, actually. At least in SPICE modeling, it doesn't affect it too much. I'm sure it affects it badly at UHF, but down at HF, it's pretty insensitive to that. So I set it up to measure the noise figure for a Hermes module with an ALEX module. The Hermes module, my estimate was it would have a noise figure of about 6.5 dB. And then the ALEX module, you go through actually 6 relays between the antenna connector and the RF connector over to the Hermes, and you go through some 5-section low-pass filters. So there's a few dB of attenuation there. I was able to measure the noise figure of the Hermes plus ALEX combination. It was about 8.3 dB on 80 meters. and it was about 8.9 on 10 meters. And so allocating a few tenths of a dB per relay and a dB or so for the low-pass filter, that's in about the right range. It turns out that the cosmic noise at 30 megahertz is about 15 dB excess noise. So if we achieve 10 dB noise figure on the receiver, we're not going to be limited by anything except the cosmic background noise. So a 10 dB noise figure objective is okay. I expect that we'll actually get something closer to about 7 dB with the ADCs that we're looking at. And so that's adequate for the problem that we're trying to solve. So the way I measured that is I put the output of Hermes into GNU radio. This is a 48 kilohertz spectral sweep. And the blue line is the straight through to the receiver, and the 5 dB ENR is with that noise source turned on, 5 dB ENR turned on. And the data is 48 kilosamples per second. It's going into a 2K FFT, so the bin size is 23 hertz. And then turned on exponential averaging to as long as it will go in GNU radio, so it's a tau of a few seconds. And you can see by the display it could use a longer tau. It's kind of noisy. The scale here is 2 dB per division, and so you see it's about 1.7 dB change in the noise from turning on the 5 dB ENR, and that's where 8-something dB of noise figure comes from. So here we don't have very much excess noise, and so a tenth of a dB difference in reading results in quite a bit of difference in the noise figure computation. And so when we build the RF module, we may use something like a 10 dB ENR source instead of a 5 dB, and that will give us a much more accurate noise figure calibration. This is the clock synthesizer module that we're planning to use for the personal space weather station. We may make some changes here to reduce cost. This is the slightly more expensive version, and John Ackerman's got some ideas on how to depopulate and drive down the cost while still achieving good performance, and so we'll be looking at how to do that. The GPS receiver module, there are some commercial modules available that are slightly larger than a 24-pin DIP, but they're in that size range and fairly cost-effective. You connect them to a GPS antenna. They'll put out pulse per second, which will go over to the FPGA so that it can timestamp the samples. And we're looking at putting on an external digital to analog converter and filter and a low phase noise, temperature compensated, voltage controlled crystal oscillator in a loop here. And the loop update rate is very, very slow. It tends to basically update once per second because it looks at the 1 PPS time coming out of GPS and asks, is the time going a little bit ahead of time or a little bit behind time. So this is in actuality a very slow update process. Interestingly, this GPS receiver module has all of this internal, but they actually break out an interface to a commercially available DAC so that they've anticipated folks are going to want to do this with that chip. Then that TCXO drives a low jitter synthesizer module, so we can program up to 4 high stability, low jitter clock outputs, and these are all selectable through an I2C interface. So we can tell this module what frequency to synthesize. One of these will probably be 122.88 megahertz, which we use to run the ADCs, but we have some options to do this. Now, in looking at that clock module, the specification we wrote says that the phase noise on the clock will cause broadband, baseband phase modulation. And so the objective is to achieve minus 60 dBc per hertz at 1 hertz at a 30 megahertz NCO frequency. So that means at 122.88, it can be worse than that, but when we divide it down in that synthesizer, it'll improve by 6 dB per decade. So that was the spec. John Ackerman set up that synthesizer chip, and he measured it at 144 megahertz. And we have various programmable loop filter bandwidths on the synthesizer. And this is the phase noise output. And we can see at 10 hertz, we need to be below about minus 90. At 30 megahertz, it'll be below about minus 80 at 122.88. And a couple of the loop bandwidths, he was able to achieve that on the synthesizer part that we're looking at. And if you make some poor choices for loop filter bandwidth, you can see that close-in noise goes up. So you have this game of, if you choose a narrowband filter, you can get one set of performance curves. And if you choose a wider band, you get a different set of performance curves. And so we have to sort of trade off the loop bandwidth for the kind of jitter that we get. The synthesizer chip, I don't have the capability to measure phase noise, but I can measure Allen variance on the chip. And so the blue line is the Allen deviation of the output. And for about 5 or 6 different reasonable frequencies, the output, the Allen deviation of the chip all fell right on top of the blue line. I then went in and picked a particularly hard to synthesize output, and basically the ratio of 2 prime numbers, and told it to put out 10 megahertz times the ratio of 2 prime numbers, which drives the synthesizers inside that chip absolutely bonkers. And that's the purple line here, and you can see the Allen deviation degrades when you pick that particular one. Every other, the reason I put that is otherwise it's a very boring graph. It's just a blue line on top of a green line, top of a pink line. So that particular one was bad. The normal frequencies fall right on top of that line. One of the interesting things that John Ackerman found, we used a commercial GPSDO module, which has great specs. When you look into the details are ugly. And so this is the output of the GPSDO, and what you can see is that the units down here are seconds, and each increment is about 150 seconds or so. And it turns out what's going on is this chip is dithering its own internal oscillator. And so it goes up and down about 60 parts per billion over seconds of time constants. The average frequency is absolutely correct in being locked to the GPSDO, but over 10-second time periods, it's 60 ppb up and then it's 60 pp down, and that causes huge phase swings in the clock to the ADC converter chip, and it totally destroys the phase coherence of the chip. So it's a great idea, it's very low cost, and it doesn't work. And so that's where we decided that we really are probably going to have to put in our own TCXO, our own DAC, and our own filter, and smooth it with a very, very long time constant low-pass filter in order to make it work. The magnetometer, we've looked at this magnetometer made by a company called PNI, and you can see the size here. It's about the size of a quarter. And there are 3 inductors, 1, 2, and 3, and they're all mounted orthogonal to each other so that we get 3-axis field measurements. And there's an there's a chip up here that will support I2C or SPI. And it turns out that we want to put it into the I2C mode. So the data engine has this PMOD connector. We have a small module at the Space Weather Station, which is the local cable extender and power injector. And so it injects current limited 5 volts DC with a SPI interface that essentially generates balanced differential I2C. It goes over, now I called this an Ethernet cable, and I was corrected. Please don't call it that. So what it is a Cat 5 or 6 cable with 8 twisted pairs that's got RJ45s on each end. And if you go down to Best Buy, they called it an Ethernet cable. But it's so we didn't want to reinvent a custom cable. You just go plug in a cable. It can support up to 30 meters, a 100-foot cable. and it takes 5 volts out, and then at the remote extender, we drop 5 volts down to 3.3, and the magnetometer sensor plugs on to that extender module. And so you have a little plastic box and a 100-foot cable, and there's nothing else required out there, and that gets that magnetometer out away from stuff. And interestingly enough, if you use steel pins to plug this onto that, it screws up the magnetic field measurement, so you have to use brass pins, and so there's some interesting requirements. It's a pretty sensitive device.
The I2C chip doesn't affect the magnet?
Hopefully not. Hopefully not. The I2C chip, you can see there's not very much metal in the chip, right? And it will plug in through some carefully controlled kind of metal down to a baseboard. And it's built using the same kind of technology that this circuit board is. It's just normal copper. Certain metals are not very magnetic. Copper is reasonable choice here. But it's all I squared C all the way out through and back, so we can talk to the magnetometer. So variance. One of the problems of using a single channel garden variety GPSDO is that interesting space weather happens during the times that GPSs go off the rails, right? So you want precision timing during that point of time where you can't get precision timing. And one approach is to use a GPS dual frequency module where you listen to the L1 carrier at 1.5 gigahertz and you listen to the L.2 down at 1.2, and you look at how do those react differently to one another. John talked about that during his talk yesterday morning. And from that difference in information, you can improve the accuracy of the GPSDO. So you get improved PPS timing during ionospheric events at a significantly higher cost. So the idea here is that we'll put in an L1 only during the phase 1 weather station, and then if the scientists say during a later observation interval we want better quality time, well then we only have to change the clock module to a dual channel clock module, and the cost to upgrade the instruments only the incremental cost of that new clock module. We may want to upgrade the VCXO for better holdover performance. That increases the cost because high stability VCXOs cost a lot more money. Or maybe we want to downgrade and delete the GPS receiver. So we have a couple of options there. Provincial variants for the RF modules. Scotty talked about single channel receiver, single channel transceiver, single channel transmitter, VHF and UHF transceivers, and maybe a dual receiver plus a single transmitter on one, so you can do things like adaptive pre-distortion on the transmitter to reduce the amount of outband distortion. That's already being done on OpenHPSDR. We're going to start with the dual channel receiver. Variants in the data engine are higher performance and larger FPGA, which significantly increase the cost, the power, and we can see modes where we may want more of the raw data, and that's going to require a 10 gigabit Ethernet interface. A 2-channel RF module at 122.88 is putting out around 4 gigabits per second of raw data, and that's a little bit tough to handle around most ham shacks. So the first version will have just data going into the FPGA. We'll down convert it, decimate it, reduce the bandwidth, improve the dynamic range, and the FPGA does all of that processing so that the data that's sent over to the single board computer is a much, much lower data rate and is something that we can affordably throw onto disk to record events. The documentation right now, all the documentation's at TangerineSDR.org. We have interface control documents which define the connectors and the pins and the module form factors for the clock module, the magnetometer, the 2-channel receiver, and the data engine ICD is in process. We have requirements documents for the clock, the magnetometer, the 2-channel receiver, which are the analog specifications. There's quite a few TBDs in there, but we're working those off with time. And the data engine's a process. We have an objectives document. Yes, sir.
I just want to remind you, it's .com.
.com. Okay, .com. Okay, so we need to go quickly get .org so we can redirect it. It's all open source. Hey, I got it right on this slide, .com. How about that? Yeah. So we have documentation, specifications, email, list transcripts, TeamSpeak recordings, meeting notes. We take meeting notes for every meeting, and they get posted up there. We'll open up a public Git repository once we actually have Gittable content. We don't have any right now. The TeamSpeak sessions are Monday nights. For those of us on the left coast, at 6 o'clock. It's 01 UTC during USA daylight saving time, and during standard time it's 02 UTC, because those of us in North America are clock challenged, and so that way it's always 6 p.m. and always 9 p.m. and we don't have to worry about whether we're on daylight saving time or standard time. And then TeamSpeak at TangerineSDR.com:7388. There's 2 meeting rooms there, and all novices show up in the wrong one because it's the default room. And so we know if new people have showed up because they're in the wrong meeting room. And then we can teach them about how to fix Vox and how to set up push-to-talk. Please do not use Vox, because Vox echoes. And it drives, some of us are intolerant of echoes when we speak and we stop talking. So anyway, that's it, and we have time for questions, I guess, Steve?
Absolutely. Hang
Okay.
on. Coming up.
Excellent presentation, thank you. This may be more of a software question than a hardware question. When you're talking about time and the GPS signals coming down off the bird,
Yes,
and that the ionosphere can mess it up,
yes.
what provisions, or has anyone thought about to say, I've got something coming down here, but I know the time is no good, it's blown.
Yes.
So to say, I have data, but I cannot rely upon the timestamp. Is there now, or will there be a provision to detect that the timestamp is no good?
Yes, that's in the documentation already. There is a bit for loss of lock, or we're in holdover, and there's messages from the GPS about the time. So we have, at least in the clock objectives module, an interface for declaring that the GPS time is out of bounds, so that when we record that data, the GPS time will have an invalid. Right now, the specification shows that we're going to use 64-bit NTP time format timestamping in each packet, so each packet will have the 64-bit NTP timestamp, and there's a way to mark that timestamp as being an invalid timestamp that will be put in the packet that's sent over.
So Tom, I just wanted to say one thing, that it looks like Tom is responsible for just the RF board, but I want to publicly say thank you for all of the documentation that you've done. If you look on the TangerineSDR.com website, if you look at the documents, a lot of them have your name on them, and they are excellent, and they are, we wouldn't be able to do without them. So thank you, Tom.
So Tom, I have a question. Antennas.
Yes.
So there's been a lot of discussion about antennas, how they get set up, because when these stations go out and get set up, there's going to be instructions on best practices. So what about the antennas?
We've looked at a couple of antennas. Currently, the space weather folks are using these high impedance whip antennas that go into an amplifier that's mounted on a ground post. And those have pros and cons. They're wideband, and they may be somewhat sensitive to ground conditions in that their absolute field sensitivity is somewhat. We would like to put together a process for trying to understand the antenna calibration. One of the people on the call is doing this in Arizona. Another option is a wideband loop, which we thought might be less ground sensitive. We've been advised that may not be true. They may have some ground sensitivity. But we're going to try to put together at least a campaign to go out and measure field sensitivity of a couple of antennas before recommending which of the antennas folks should use when deploying the system. The difficulty with antennas is we may get quite a range of absolute receive sensitivity depending on how the antennas are set up.
Preferred antennas for 130-foot towers phased, right?
Yeah, right.
Okay.
Yeah, this is a great presentation, primarily focused on the hardware, but obviously behind all this hardware is a lot of software and firmware. And it reminds me of Ken Olson's famous comment that it's just a small matter of software. And in this case, how much of a small matter is it? How much reusable software is there out there for this, and how much new software is going to have to be developed?
Yeah, Bill is leading up the team that's working on the software, and most projects that I've ever been involved with, the hardware gets defined and started quite a bit ahead of where the software gets started. And I think the reason for that is that it's difficult to put together a lot of the software pieces and functions without knowing what the hardware is going to do. And so naturally, most programs tend to have a fairly upfront a hardware definition phase and then a software phase, which is partially what do we want to do and what limitations exist in the hardware that we have to deal with and work around. And this project seems to be following kind of in that exact same mode. So the TeamSpeak calls have been very hardware focused. I think those will transition over to a much more software focused discussion as the hardware comes online and we find the warts and all of the issues that we're going to have to work around.
Even right now, last night we actually had a design review, a specification design review for the different software packages. So we're not talking about it so much today in these presentations, but there are already specification documents written. They're on the web. They're going to go under iterations this week based on the input that Bill got last night. So these are all things that we are working on actively.
Okay, other questions? Thank you very much, Tom.